Today we'll talk about the stability of those schemes for the advection equation. And before that, we will have to settle on the boundary condition for this problem. When we discussed the characteristics, we used infinite domain. All right. So, for example, for A is positive, okay. A is, again, this is ut plus aux is equal to 0 with some initial condition. All right. So when A is positive, the information is traveling like this to the right. Okay. So the whole initial function is travel like that. It's transported to the right like that. Of course, in real life and in our actual computation, we're going to have a finite domain. Let's say as we were doing from 0 to 1, and we have two boundaries. Right, have two boundaries as time goes up. So this direction is x, that direction is t. Okay, that's t. So as you can imagine, the question is, what kind of boundary condition should we specify? Okay, if you think about it, because once you have the initial condition, so basically the initial condition tells you something about this side, right? That's the initial condition, or time is 0. So which means when you have you have a point, okay, and you know its value, because you just evaluate the initial condition at that location, so that the information would travel like this, okay, like this. And so the value here is equal to the initial value there. The 2 points here are the same, have the same value. So, and in that case, I hope it's pretty straightforward to state that you don't want a boundary data for that location, because otherwise, if the boundary data you give happen to be different from the initial condition, the corresponding initial value, then you're violating this property of the PDE, right? So you want to be careful what kind of boundary condition you specify, essentially. Similarly, so a point here will be transported to there, right? So you don't want to specify the value here, and so on and so forth. So the extreme guys is here, okay? The initial condition at 0 would be transported here. And of course, this goes all the way even to here, right? So in this case, there's a concept of inflow and outflow, right? Outflow. So when A is larger than 0, right? In this case, the information is traveling to the right. The left boundary is the inflow. So the information is coming from there, which is for here, right? For here, this will be the inflow. You do need to specify the value here, otherwise you don't know how this would be traveled, right? So you need boundary data for that location, okay? For the one on the right, you don't need the boundary data. When A is larger than 0, the left boundary might be the RY boundary, which is x is equal to 0. That line is inflow boundary, okay? And x is equal to 1. That's outflow. As you can imagine, when A is less than 0, it's negative. The information goes towards that direction. Okay. So in this case, x equal to 1 is inflow, but x equal to 0 is outflow. So the boundary condition should be given just on the inflow boundary. Okay, boundary. Another way to take care of this situation is without differentiating the inflow and outflow, is to use a periodic boundary, so-called periodic boundary condition. What it says is that the information goes to the boundary and then comes back, basically. It's period, right? It repeats themselves. So let me try to use a picture to explain that. So basically here, right, here is x0, and for positive A, it goes to there, right? It goes to there. And then because the boundaries are the same by periodic, it means, the period, the two ends of the periods are the same, which is our u in the format of uxt. So it's u0t is equal to u1t for any t, all right? In particular, this value, so this will be the u0 of x0, all right? This value is transported to the right boundary, and it's the same as this guy on the left boundary. This is also u0, x0, right? And then, of course, let's try to draw a parallel line. This is also transported there, okay? And another line, if you have x1 here, so that will be transported here, and this will be treated the same because it's a periodic boundary, and then it's transported here, okay? So that's the so-called periodic boundary condition. I hope that makes sense. So for analysis, we're going to use continue adopting the method of lines approach that we explained, and then basically turn PDE into a system of ODEs. Feel free to revisit that particular video. So the method of lines is that on the domain 0, 1, all right, we're going to have x0, x0, x1, x2, xm, here is xm plus 1, all right? So we have these guys, or this guy is denoted by um plus 1, t, u1t, u0t, all right? You fix the corresponding x value, and it becomes a single variate function of t. All right. So what we just talked about is a periodic boundary condition. Basically means that you are going to glue the two endpoints, which is u0t is always equal to um plus 1t. These two functions are the same for all the t. Okay. The left boundary and the right boundary are the same. So, which means that you don't need to solve both of them. You only need to solve your u1t all the way to um plus 1t, right? For the elliptic case, we have the Dirichlet boundary. We know the value of u0t and um plus 1t, so only need to solve u1 to um. Now, for the advection, it's different. You give one boundary condition. It's either just on the inflow or the periodic. So we need to solve one more, u1 to um plus 1. And u0 is the same as um plus 1 for the periodic case. How do we proceed with the method of lines? Again, that's basically, we have the ut plus aux is equal to 0. That means that u sub t is equal to negative a u sub x, all right, u sub x, and what we do is that we're going to see what that means at each location. So for all this j, for any this j, right, j is 1, 2, all the way to m plus 1. What we have is this uj, right, the ujt, okay, this ujt is at ujt, all right. If you take the prime, that's ut, u sub t becomes uj prime, okay, add xj. This guy should be equal to negative a ux, this again add xj, okay. So for our fourth scheme, we use a centered scheme for different ux. What this says is that we're going to denote this by negative a uj plus 1 of t minus uj minus 1 of t divided by 2h, right? For the fourth scheme, the scheme 1 that we talked about in the last video. So you know the drill, then the idea is to try to write this as a system, right? A system, and come up with that little matrix A. So this is true for any j. Let's try to write them down. When j is 1, right? When j is 1, we have this u1 prime t, okay? This is equal to negative a. We have u2 minus u0, right? u0 divided by 2h. But we know u0 is just um plus 1 divided by 2h, right? When j is 2, we have u2 prime t. This is negative a 2h u3 minus u1, right? So all the way to when j is m plus 1, we have um plus 1 prime t is negative a. Here you are going to get um plus 2, right? Um plus 2 is j plus 1. Um plus 2, um plus 1 is like 0. So move one more point to the right, that's like 1. So it's u1 minus the left point of um plus 1 is um divided by 2h, okay? So we just need to turn all these equations into a system, right? As we did before. So going to get this u1t all the way to um plus 1t. This guy prime, okay? The first equation give us first line, first row. Second equation give us second row, and so on and so forth. So first of all, they all have negative a over 2h outside. Okay. So we're going to move this to the next row. Let me move this like this. So u1 is negative, and then you should put a 1, and this should be multiplied by of course u1t to um plus 1t. All right. So for each j, there's no uj, so that's just 0 all over the place for the main diagonal, right? For u1 prime, you should put a 1 at u2, negative 1 at um plus 1. So it's 1 at u2, negative 1 at the very right end. That's it. Everything else is 0, right? For u2, you should put a 1 at u3 and a negative 1 at u1, and so on and so forth. For um plus 1, the very last one, you should put a 1 at u1 and a negative 1 at um. Okay, of course, second row from the last will be 1 here. So the sub-diagonals are 1s and then negative 1s. And then, of course, we shouldn't forget about what's different from the elliptic case is that now we have little negative 1 on the upper right corner and 1 on the lower left corner. Okay? Corner. So that is A, and if you denote this guy by capital U of T, right, it's a long vector, and then the left side is become U prime of T is equal to A times U of T, right? So that's the ODE of the topic for 361, and again, we can use all sort of different things to solve. And what we're going to show is that the first scheme that with forward Euler in time and centered in space, the scheme 1 here is actually not stable. That we noted last time when we introduced the scheme. Now we're going to see why, okay? So this, we again need this stability region for the ODE solvers, right? For the forward Euler, we know that the stability region is actually this circle, right? Here is -1. This disk, okay? So the eigenvalue of your A times delta T should be within that disk, okay? And if you look at this matrix A, right, matrix A, what is this? A is just negative A over 2H of this guy. You have 0 on the main diagonal. This is M plus 1 by M plus 1 matrix. And you have 1 on the sub-diagonal, and then -1 for the other diagonal. And you have a -1 here and a 1 there, right? It's pretty easy to see that A transpose is equal to, if you transpose it, you get -A, okay? You get -A. If you remember a little bit of the linear algebra, this means that this is a definition for it being asymmetric. When A transpose is equal to A, that's called symmetric. Now it's kind of like anti-symmetric, asymmetric. It's not symmetric. It's one particular linear algebra result is that for symmetric matrix, if the transpose is equal to A, we know its eigenvalues are real, okay? And when this is what we did was the elliptical case. We derived its eigenvalue, and it is actually indeed real. And when it's -A, there's a theorem in linear algebra says that the eigenvalues are purely imaginary. Purely imaginary. What that means is that the eigenvalue lambda for A is always going to be equal to I times something, right? Times a real number alpha, okay? And this basically shows that we're in trouble. The first scheme is not going to be stable. Because the I times alpha, the purely imaginary numbers, where are they? They are basically like here, right, along the imaginary axis. This is not inside of that stability region we just plotted. This is not inside here, okay? This is it's not going to be inside there. There's okay. So like the numbers right here, so there's no way they're being contained. There's only one point that is contained in that region, which is 0, 0. Everybody else will not be contained in it, so it will be unstable. So this concludes that scheme 1 for ut plus aux equal to 0 is not stable, right? What we noted when we introduced the first scheme in our last video. Of course, assuming we're going to assume that you forget about that little linear algebra theorem. You don't know is eigenvalues are purely imaginary. Then actually, as we similar to what we did for the elliptic case, we can actually derive the eigenvalues. That's what we're going to do next. Okay, we're going to use the similar approach we motivated and described last time when we dealt with A for the elliptic equation. So we're going to use here. We just need the V to be let's say periodic on 0 to 1. Let's say we're going to use e to the I 2 pi with a frequency let's say px, okay, x from 0 to 1, and let's try that and see what is if it's possible to have a neat eigenvalue coming out of it, which means v of xj is going to be equal to e to the I 2 pi p. My xj is jh, okay, jh. xj is equal to jh. h is equal to 1 over n plus 1, okay? So then we just need to figure out, okay, we need AV is equal to lambda V, all right? So we need to look, which means we need to look AV at the jth component is going to be equal to lambda times the V at the jth component, right? For any j, okay? If we can confirm that, we know the eigenvalue lambda for that corresponding eigenvector, eigenfunction v of x. So what is AV? J, and it's j's location, which is negative a over 2h, right? J's row is j plus 1 times minus a j minus 1 divided by 2h thing, right? What I just did. So we have a one. You have basically just v at j plus 1 minus v at j minus 1, right? So this is a over 2h. You would have e to the I 2 pi p j plus 1h minus e to the I 2 pi p j minus 1h, okay? This is pretty easy to simplify because we're going to get a over 2h. If we factor out the I to the e to the I 2 pi p jh, what we have left is e to the I 2 pi ph minus e to the negative I 2 pi ph. Okay? This guy is nothing but the Vj. So there you go. We get this lambda, right? What's left is just our lambda. So this is lambda times Vj with lambda being negative a over 2h, and e to the I times something minus e to the minus I times something is just I, right, times 2 cosine theta plus I sine theta, 2 sine of that theta, which is 2 pi ph. This is going to be, we're going to cancel the 2 with 2 with negative I, and we have a sine 2 pi ph divided by h. So those are the eigenvalues, okay? Those are the eigenvalues. Negative I again, a sine 2 pi ph divided by h, alright? And let's multiply. This p can be equal to 1, 2, all the way to m plus 1. This would be the eigenvalues of A, of our A here, right? Of that Fermi matrix. Okay, negative A over 2H 0, 0, 1, 1, negative 1, negative 1, and they have little negative 1 here and little 1 here. Okay, it's a matrix. So we're going to refer to these numbers again next time, the next couple of times. That's something to keep in mind. In particular, it's pretty obvious to see they are all purely imaginary. So that confirms with our linear algebra result. If A transpose is equal to negative A, I mean, we didn't really prove that linear algebra theorem, but it confirms in our case, our A happened to be asymmetric, and it indeed only has purely imaginary eigenvalues. And again, so that is impossible for all of them to be in the stability region for the forward Euler. Okay? And we're going to show next the leapfrog, like Friedrichs, like Windroff, actually stable and I mean with some condition. So some of them we're going to leave as a homework, but the rest we will analyze and then we'll see how they are related. Okay.